So welcome back. Well, you've been here the whole time. I'm back. So here's an outline of where we're going to go. I got asked to talk a little bit about a few recent and upcoming heliophysics missions and their traceability matrices. The way I've interpreted that is I'm going to just give you a little glimpse of some recent and upcoming missions, and then jump into the real meat of the talk, which is traceability matrices and why you actually care about them. Uh, it is a trope that young scientists in particular, but scientists in general, hate these things. But I in my career have found them to be extraordinarily important. Um, you don't know who I am. Many years ago in 1995, I was working on the SOHO mission. Uh, in 97 or 98, I got an offer to become a civil servant at NASA Goddard Space Flight Center and chose not to take it, which everyone thought I was crazy for at the time. I took a career instead in soft money funded science. And the thinking that went through my head was I do not have the personal discipline to carry out science unless I have to go through the proposal process. And so I've spent my whole career proposing each bit of science I want to do a year or two at a time. And that process has helped me immensely by forcing me to formulate exactly what I want to do, how I intend to do it, and what I expect to find. Now, has it always played out that way? No, not in your life, right? But the exercise of doing that is critical to being able to carry on science. And so whether you choose to lean on that crutch of having to propose and sing for your supper, if you will, or go into another position like a professorship or a hard money position if you can get it, uh, is really up to you. But however you steer your career, you have to do this stuff. And so I'll talk a little bit about how it works and how that applies to a mission, and by contrast to a mission, anything that you do on the grant scale of one or two people working on something for a year is going to seem really easy by comparison. So don't be afraid, but buckle in. All right, so here's a few recent and upcoming heliophysics missions. You already heard about the HSO earlier today and some of the ones that are here. I'm just going to run through a few of my favorites that are things that people in my circle refer to a lot. Solar Dynamics Observatory, you've heard a lot about it. I showed you data from it yesterday. You heard about it today. The GOES, it's another mainstay of coronal imaging in the EUV. Solar Orbiter is a really big one. It's an ESA-NASA collaboration operated by ESA in this really exotic orbit that gets it close to the sun, and it's going up out of the plane of the ecliptic so we can see the poles of the star. Really neat stuff. Large suite of instruments. Parker Solar Probe flying through the corona, sampling stuff. We get all kinds of great results out of it. You're likely to use data from this mission if you carry on in the field. Punch, that's my own mission, very near and dear to my heart. Now we're into things that are recent. Punch just launched. We're still in commissioning, but we are pumping data out. You can, if you are bored with what I'm saying, you can go on the web right now and download Punch data and have a look at it. See what the heliosphere looks like right now. Codex is another recent coronagraph. It's on the ISS right now. It is a coronagraph that doesn't just use the K corona, like I was talking about yesterday. It uses a forest of lines in the Fraunhofer spectrum that are distorted in different ways by different parts of, or in different parts of the spectrum. They're distorted in different ways by the flow of the electrons. So by looking at brightness ratios in particular narrowband filters, they can diagnose the temperature and the outflow rate of the plasma in the corona. And that's a different measure than just seeing a feature go by. A feature could be a wave, it could be a caustic, some kind of weird effect like a barber pole moving by. But if you get a spectral signature, you're actually measuring the physics locally where the light's being scattered in the corona. So that's really neat. Tracers just went up. They're in commissioning right now. That's an in situ pair of spacecraft that are trying to understand the terrestrial effects of the solar wind by sampling it at 2 different times. They have twin spacecraft, and they're going through commissioning right now. Padre, again, really neat stuff. It's a CubeSat. It's going through commissioning. This is an X-ray polarimeter. So, Punch is doing something easy. We're measuring polarization of white light. Polarization of X-rays is hard, and they're doing it in a CubeSat. So really neat stuff. You're likely to use this if you're interested in solar flares. Cubix, this is being built out of Southwest Research. It's another X-ray instrument. It has some full disk spectrographs that can measure the sun as a star in the X-rays, so you can see flares and nanoflares and various interesting things, but also it has a spectral imager on board. It's all crammed into one little CubeSat package. Really neat stuff, scheduled for launch in 26, so in development now. Sunset, another CubeSat that's scheduled for launch. I showed you those sous vide campaign images the other day, yesterday. Seems like forever ago. So Sunset will cover that field of view all the time. It's a dedicated instrument to study how coronal mass ejections evolve as they move out. Because it's looking in the EUV, it can see things like shock effects that are very hard to see in white light. So again, watch for data from this once it launches, hopefully in 2 months. There are a lot more, but that just gives you a smorgasbord of the kinds of things that are on the horizon. We have a lot of missions that are rolling out the door. We have a lot. You saw the fleet from the Heliospheric Systems Observatory earlier in the day. Each one of those has a person like me behind it, right? One person who had an idea gathered a team and organized that team to produce something great for the science. So what are those missions for? Well, we can think of science as a 6-step process. This goes all the way back to junior high, right? We've all seen this. This is the scientific method. You start by stating a problem, you formulate your hypothesis, you design an experiment, collect data, analyze that data, and draw a conclusion, and voila, you've made the world a better place. Well, we do that. Missions are designed to attack this part of that method. It's the 6-step method to science, and the missions are an experiment to address particular science questions. Now that's a different question. Yesterday we talked a little bit about how do you use these things? Well, once they're on orbit, missions are totally different. This is how you design a mission, right? This is how you use a mission, right? Science isn't really just a 6-step process and it's done. It's more like this circular process with hypotheses and observations and new hypotheses and theories all kind of interacting with each other. So once a mission is on orbit, you want to make observations with it, and you'll formulate your own 6-step process. I have an idea about the sun, or maybe I looked at some data and got an idea, and now I'm going to test that using the mission. The mission then becomes part of the tool set that you have to address new science. But that's not how we design them. We have to design them in order to address particular science goals. Why is that? Well, we'll get into that in a moment. How to design a mission. Here's why. Missions are expensive. If you set out to do any large project, you have to have an endpoint in mind. You have to know what you're doing, why you're doing it, and when you're done. When you're done is really important, and it's hard. If you've been through graduate school, you know your first paper is extraordinarily hard to get out the door, right? Because you're doing work, you're probing the secrets of the universe with your advisor and your research team. How do you know when you're ready to write up, right? There's always more. So how do you know you've reached a breaking point and you can write it and publish it? Well, the first couple, your advisors and colleagues tell you. After that, you can sort of get the hang of it and move forward. But for a large project like a mission, particularly if it involves a new instrument, it's very easy to just keep going and never finish. And then it's like you never started. So you have to know what the endpoint is and aim for that. So we design missions and individual investigations at the graduate student level around this 6-step process. We state a problem, right? You look at whatever resources are available. Maybe your advisor dictates it to you. Maybe you read some literature and get interested in a particular problem. You state the problem and try and refine that statement until you have something pithy and actionable, right? Not just, what if there were TARDISes landing on the sun, right? That's that's too vague, right? Maybe you want to say something along the lines of, is the corona heated by turbulence or is it heated by reconnection, right? That's an either or question that makes it easier to solve, right? That's the kind of question you're looking for. So you got to figure out, is that question compelling enough, right? At first, as you're refining this, you want to see if it's compelling enough to warrant your time or someone else's money. If you're independently wealthy, maybe it's your money. But the one thing you have that you'll never get more of is your life. So do you as a scientist want to devote a year or more to solving this problem, right? And if it's compelling, then maybe you've got something. For a mission or observatory, that's a larger project. And so you have to have a suite of problems, right? You want to have a bunch of stuff that's going to light up a large number of people in the community because we're all devoting a significant fraction of the resources that are available to the entire science community making one of these things happen. Once you've got a problem, you formulate a hypothesis. Well, it's more complex than just the 2 words on this diagram. You want to think about how to solve that problem. What do you need? And the hypothesis could be some new model, or it could be that you want to compare between existing hypotheses. Or it could be just, I need to learn more about the system, right? Does this system actually have a pattern in it? That's a hypothesis. You have to have something that's testable and can reach closure, right? That's an important thing that we all learned about back in, high school or something. A hypothesis is a question that can be answered. It's not vague. So forming that question is important. This is the step that I had trouble with as a young scientist. I was really interested in all these systems and I would dive into them and just look at them and find patterns, and it was really cool. But I didn't, for a number of years, have a good sense of what is a hypothesis that I can formulate and stick to and answer. That's actually the first guidepost, right? If you want to know when to write up your results, did you get to an answer or at least to advancement on your hypothesis, right? That's how you know you've reached a breaking point. Well, design your experiment. This is really where traceability enters for a mission or for an investigation. What are you going to do and what's required for you to do in order to get at that hypothesis, right? I have to observe the corona. Well, okay, you can see that in an eclipse. You can get hints of the corona just by sticking your thumb in front of your eye on a very clear day in the mountains. Is that good enough? Well, I don't know, right? So you have to design the experiment, you have to develop requirements for what that experiment needs to do. What kind of resolution do you need? What sensitivity do you need? Do you need wavelength sensitivity? Then in the process of designing, you have to iterate until your experiment actually can make those measurements. And if you can't reach closure, maybe you need to back off on the measurements, see if you can be more clever about how you analyze. The big problem face is that you start with a nebulous idea. I need to address this hypothesis. And you end up, if you're building an instrument, with how many screws do I need to hold in the occulter on my coronagraph? Right? Or if you're in the lab, I'm trying to probe the secrets of the universe. How do stars in general make ultra hot atmospheres? And what I can't do is get my code to run, right? You have to bear all that in mind. And if you have a set of requirements that can guide your mind and keep both of those scales of question in mind at the same time, so you can take small actions in the lab or in front of your computer and be making progress toward the larger goal that you set out to address. There's lots of there are lots of sayings about this in the public eye, right? I mean, when you're up to your neck in alligators, it's hard to remember you're here to drain the swamp. But as a scientist, your job is to remember that you're here to drain the swamp. And you may be doing a million things, fighting alligators, learning about how mangroves work, digging a dam or digging at the dam to let the water flow. Whatever you're working on, all of that is towards some overarching science goal. And what helps you remember that? Traceability, what we're talking about here, and specifically the requirements of your investigation. Okay, you're going to collect your data. It turns out that's an important part of your experiment. I see a lot of work where people come up with a great idea. I'm going to build a coronagraph, look at the sun. I'm going to address these questions with that coronagraph. Of course, coronagraphs can see the stuff that I want to see. But then what do you do with it? Now you've got an instrument and you've got a sun. You have to connect the dots, right? You have to actually point that thing at the sun and collect data and do something with those data. So planning for that is important. How much data do you need? How will you operate your experiment to make sure that the data you get from that experiment are right, or at least address the hypothesis? And this applies not to just instruments, right? It could be a simulation that you're working on, or a fancy new image processing scheme that can drill into what active regions are unstable and likely to erupt, right? People are working on problems like that with AI right now, right? So you have to think about, how am I going to validate my AI, but also how am I going to use this capability that my model or my instrument gives me? For Punch or SDO, pretty straightforward. We set up our experiments in such a way that we could just run them forever. Right? SDO just takes an image every few seconds and downlinks them all and disseminates them to the community. And you can bet that although right now it ends there, they're distributing the data, when they proposed to build SDO, the SDO team were fully on board with connecting all the way around this diagram. SDO was launched to address particular questions, and that included forming a science team and giving them the tools and the instructions for how to pull the data that they needed to address those science questions. So you have to connect the dots all the way to the end. If you're writing a small proposal, it's the same thing. If you're writing a 5 or a 15-page proposal to NASA ROSES or an NSF proposal, a lot of what the reviewer is going to do is make sure you connected all those dots, right? And that's a service to you as a scientist. That's why I stayed in soft money my whole career, because I knew that my peers would help me by forcing me to connect those dots with every program that I ran. IRIS is a spectrograph, and it's very limited. It can't just take spectra of the whole sun all the time, and so they have to run campaigns. They do weekly planning, and they actually had to plan as part of the mission, bringing people out to operate and make decisions about where they're going to point their spacecraft this week. DKIST, I didn't talk about it in the list of missions because it's ground-based, but DKIST is an observatory. We used to call it the Advanced Technology Solar Incinerator. It's a 4-meter diameter primary mirror telescope at the top of Hawaii. And they have a telescope allocation committee. It's such a large installation, and it can do so much science that they actually compete the science periodically. And if you want to use the DKIST, you have to go and defend that science to a board of scientists who will allocate time. If you have a new solar simulation code, how will you operate it? We talked about that. Catalog of observations. If you are trying to do something statistical with the sun, you need to think about how you're going to catalog all of the things that are relevant that you find on the sun. Observer bias is a thing. If you just look for particular types of feature, well, that's great for an initial survey. But if you want to find out, for example, do active regions tend to twist around as they emerge or stay horizontal, and do twisting ones flare more? Well, you better have some way of selecting features on the sun that's bias-free, or at least that has controlled bias. So catalog of observations. Analyzing your data. Did I kill this thing? It's this is not working anymore. Can I just tell you to go forward? Let's see. Oh, no, it's working. Okay. Excellent. Thank you. All right. Analyzing your data. More of the same, right? We talked about collecting. Oh, I think. Oh, is that it? All right. Okay. Thanks. Next, please. All right. So data analysis, what are you going to do with it to close the science? Okay. Now you've got your data in hand, your catalog, your whatever. How are you going to actually manipulate that data and distill out an answer? Again, you do that. That's just what you do as a scientist. But if you're planning your work, you have to actually think in advance about how to do that. Next. All right. Many is surprisingly hard, right? How do you think through what it is you're going to do to get to the end? Next. Next. All right. So you have to plan the resources that you need as well as what you're going to do. Let's keep going. And then draw your conclusion. Next. Next. Okay, so a traceable plan or a traceable investigation connects all six steps of this diagram. And at the end of every successful proposal I have ever written, and there have been a lot of them because I've been doing this for 30 years, I always end with, next, a closure section. I start out with some grand ideas about what I want to do. I distill it into a well-formed question that I can address. I spend most of that proposal talking about how I'm going to address that. What are those middle four steps? 1, 2, 3, 4. Yeah, 4. And then at the end, I come back with a little section that says, I'm going to connect all these dots. I'm going to address this hypothesis by building this experiment, operating it in such a way that I'm going to get the data. I'm going to do the steps that I outlined above to the data, and that's going to let me answer this question, right? Bring it around. That's why this diagram is almost a circle, because at the end, you have to close all the steps and demonstrate that you have built a complete pathway to closure. That's how you plan a mission, right? And we're going to walk through that for the punch mission, but it applies to almost everything you do as a scientist. You should be able to do this in your head. And in a few years, you'll wake up in the morning and this entire process will spring full formed into your head in the shower. Some kinds of question. But in the meantime, you have to practice it. And the younger Craig DeForest went into soft money science because I knew that I didn't yet have the discipline to think this way. Next. All right, it's modes of instrument design. Many people might say, well, look at all the historical instruments out there. Those weren't built with requirements in mind, and they opened whole fields of science. Next. Next. There we go. Okay. So this is something I promised you yesterday. This is a picture of the very first coronagraph ever built. It's right next to Russ Howard, who is the PI for almost every coronagraph that's flying, other than Punch, or was at one time. He's handed most of them off to other people. But that is a coronagraph. That is the very first coronagraph ever built by a guy named Bernard Liot. It's on display at the Observatoire de Paris. Next, please. That's the real thing. That's the actual coronagraph. And you can see it looks kind of cruddy. I mean, Liot was a brilliant man, and he built it in about 1920, some thereabouts, out of whatever was on hand in the laboratory, which means it's made of wood, scraps of wood, and they're held together, with glue and nails and things. And he assembled that by hand. Next. Okay, there we go. Next one. There we go. Next. It cost about 1 year of his life to do that. And there is no requirements flow in the documentation. He wrote papers about, I did this thing and it's great and it works. And now there's this new field that's open. But we don't know very much about his thinking that went into building that, in the sense of tracing those elements. At that time, that was just part of the expertise that people had. But now, everything's harder. All the really easy stuff, I'm going to go in my backyard and just build something, seems to have been done. So next. Oh, this is the inside of his coronagraph. I snuck up next to where Russ Howard is standing there and held my phone up and took a picture down the barrel. You can see one of the lenses is still there, and the walls are rough, right? They're not particularly well baffled, and they're covered with soot because he didn't want to paint the inside, so he sooted it. It's crazy stuff. Anyway, next. Okay, so this is the NFI coronagraph. It's the central part of the punch uh, suite. It looks near the sun. This is an extraordinarily complicated instrument. Next. It's very simple in the sense that we've removed all the extraneous stuff, but it does improve on 100 years of prior instruments. The complication is in the requirement structure that we used to build it that made it a better instrument. Next. The occulter is aligned with precision. Those particular ridges on the occulter, it's labeled there, those have tolerances measured in microns for their diameter. Next, we budgeted the stray light. We allocated how much stray light we could tolerate from each part of the instrument. Now, it didn't play out the way we expected, but we had that very complicated stray light budget in place. Next. Next. Oh, 10 micron precision alignment. That's the degree to which the occulter as a whole needs to be aligned. But the relative height of those ridges is less than 2 microns. It costs about 40 FTE years, 40 people working for a year or one person's entire working life to build this thing. We were not going to devote that type of resource to making pictures without a pretty damn good story, excuse my French, or why we thought it would work, right? You have to know what you want. You have to know that what you're building is going to do what you want, and you have to know when you're done, right? Because we could have spent years refining this even further, but we got to the end when it met all the requirements, and then we shipped it and launched it. Next. Okay, so the requirement flow was critical because that's how we knew when each part of it was done. Next. All right, so it's not just a matter of how many resources it takes to build something that requires, well, requirements and traceability. This is a coronagraph that Southwest built last year, or I guess 2 years ago now, called Cape Core. This is on, next please. All right, it's a new design, next. This is called a shaded truss coronagraph. There's an external occulter, most of a meter in front of a telescope, and the truss that holds the occulter in place is shaded by the occulter itself. Okay, what that means is we don't have to build that big housing around the front to hold the occulter and shield the stray light. We can just do this. And the question was, would it work? And we used careful design and low cost execution. We wanted to build a coronagraph. The hypothesis was, well, I believe a coronagraph can be built with the resources available to a bright high school student. Right? So this was a technical demonstration. And in fact, we demonstrated that yes, you can. This coronagraph, it's open source, the plans are available, and if you choose to, over a weekend, you could make one of these. Next. All right, so we used targeted precision. We had to engineer that design very carefully. Next. The total cost was less than half of an FTE year to conceive, design, build, and deploy this thing and reach closure on the write-up. So that half of a person year includes writing up the paper about it. But, next. That was only possible because we understood the requirements flow. We knew what it had to do to demonstrate itself technically. And so we could design a system that did exactly that and put it together and check off the requirements and know that we were done. We didn't have to monkey around in the lab. We could just go straight to the end because we had that requirements flow up front. So it's not just big things that cost tens of years to finish, right? Little projects benefit from really understanding the traceability. Anyway, we deployed this. We took pictures of the corona with it, and we used, I think it was $20 worth of plastic and a little bit of epoxy, plus a $5,000 telescope. But still, I mean, compared to $8 million for another coronagraph. Next, please. Okay, so let's dive into mission level requirements. I'm going to walk you through the process of building traceability for Punch. And it is scary because Punch is a big mission. So don't be afraid, just be ready. But if you can master something at this level, or even just grok it, it will make it much easier to formulate traceable requirements for your own investigations, even as you launch your career. So next. All right. Punch has a lot of requirements. We have something called the Program Level Requirements Agreement, the PLRA, that defines the mission. That is the contractual document that NASA signs up to and says, we want you to build something that meets these requirements. That includes our observing requirements. There's NASA requirements for missions in general. The MARS, the mission assurance requirements, those are the processes you have to fulfill to ensure that what you're building actually meets all of the quality specifications for NASA as a whole. That rolls down into all these other acronym named documents, and then down to what we call level 3, which is requirements that we levy on each subsystem of the spacecraft. That's pretty complicated, right? You haven't seen the half of it. Next, please. Okay, so this is the link diagram for our internal database of all the requirements, and it flows down to level 6. So at the top, level 1 requirements are big. They're things like your mission has to observe the sun. Oh, excellent. Thank you.
No, you've got plenty of time.
Awesome. Your mission has to observe the sun. And by the time you get down to the bottom, it's your screws have to have a certain pitch, right? And so in order to accomplish these goals up top at level 1, the PLRA right there, we have to define the mission. That's this MDR, a mission definition document at level 2. And that flows down to level 3, where we define the subsystems. You have to have an instrument, a WIFI and a NIFI. You have to have a microsat that supports those instruments. You have to have a science operations center on the ground to analyze the data. Starting in your head to fill in those parts on that little spiral diagram, right? There's a mission operations center that operates the spacecraft and gets the data to the SOC. There has to be, the SOC has an ICD here to the SDAC. SDAC is NASA's archive where we put all of our data. We also use it for data distribution. So this, at level 3 here, we had to connect the dots across the entire mission. Every little piece has to connect to the next one and the previous one, kind of like a row of Tinker Toys to make that full connection. And then of course, it just refines from there until you get to something that somebody can check off in the laboratory as they're building a thing. So this is a diagram that NASA uses, or I've seen several NASA missions use. It describes the process of building a large project. This is also true for small projects. It's just got less colors in it. So you start over here with your level 1 requirements and refine them and move down through requirements refinement. You spend a little time doing some stuff, and then you verify the requirements and roll them up level by level until you get to the top and you say, oh, I've built something that will work, right? And if you didn't do all that legwork up front with the traceability and the requirements, you wouldn't know when you were done. But if you did, you do. Unfortunately, this diagram isn't complete. Most of what we're going to talk about is traceability, which is how you get from the science question to those level 1 requirements on the mission. So there's an additional layer here that I just drew in PowerPoint. You have science observing requirements, right? That's what's on the spiral diagram. And that gives you a mission success or completion criterion that you can check off. If you will, it's the level 0 requirement. So the definition process at the top here is a formalized way of saying what you need. The traceability matrix connects those vague questions that you then refined into well-formed science questions to the actual top-level requirements for the mission. This is our fact sheet for Punch. This is the very top of a 1-page summary that goes at the front of any mission proposal. And even on a science proposal, you should have something like this. You should have a visual image that conveys an impression of what the science is you're going to do, just because we're all visual thinkers, many of us. Uh, and then a summary of what that's about. So those words there are our science objectives. We have two of them. One is understand how coronal structures become the ambient solar wind. Not very well formed, so we had to break that down into some questions, which we've written as topics here. The other is understand the dynamic evolution of transient structures, CMEs, CIRs, shocks. And we broke that out also into more well-formed questions that we could answer. Down here, we talked about what we're actually doing, right? This is what we set out to do. This is how we do it, right? And if you can't write that about anything you do as a scientist, you probably shouldn't be doing it. You should go back and think about, what am I about to do in the laboratory or messing around on my computer that's going to help me get at these large-scale questions about the universe. This is our traceability matrix. This is a fold-out. It's 2 pages wide. It's a total eye chart from where you're sitting. I get that. There are 2 parts to it: the actual traceability matrix and our early requirements. Those are the top-level requirements on the mission. We're going to go through them in a little bit more detail, and I'll show you how they fit together. So this is a zoom in on just the traceability matrix part. Can you read that yet or no? Sort of? Not really? Okay, I will read it at you. Let's get rid of the bottom half. So we're just going to look at one of our 2 science objectives. The way you read this is, over on the left, it has your objective and it has things about the world. In the middle here, you have the actual things you have to measure in order to close those questions. Over here, this is the data products or observations you're going to get from that. And over here, this is how you're going to reach closure. So this is the entire pathway around that spiral, minus maybe getting it to the scientist and allocating hours. That comes later. But this is the core of what you're going to investigate and how it works, right? So you start with the science objective. What are we studying, right? That leads to the science questions. They're specific and well-formed. And what I mean by well-formed is something very specific, right? You have to be able to tell when you've addressed or answered the question, right? There are a lot of questions that we ask ourselves that are open-ended. Even things that are falsifiable can be formulated in such a way that you don't know when you're done. You have to know when you're done. Physical parameters. What do you need to measure about the universe in order to answer that? So up here we have, how does the young solar wind flow and evolve on global scales? That's not known right now. How does the solar wind accelerate on scales comparable to the corona as a whole? There are lots of models, there are point measurements, but there, up until Punch, has been no systematic routine measurement. Physical parameters. We need to measure the image plane projected speed as a function of radius and heliolatitude. Basically, we want to map the speed of the wind all the way around the sun. How are we going to measure it? Well, observables. This is things you can actually measure with an instrument. We're going to look at small density inhomogeneities and their motion spanning the outer corona and inner heliosphere via Fourier spectra, autocorrelation, and something called kinematic tomography, which we went on to define in the body of the text, but I won't dwell on here. Okay, so that tells you what you need to measure in the world. The next column is, what are the specific requirements for the measurement you need to make? And we spent a long time, right? We had to break out each of these rows into our 6 fundamental measurements that describe our measurement, our 6 fundamental requirements. We iterated on that a lot. Sometimes there were 4, sometimes there were 9. We settled on a subset of just exactly 6 that were enough to constrain our measurements and define what we had to do with this mission. So spend a lot of time figuring out how you need to specify your measurement. But at the end, you have to have something that's verifiable, right? Can I build an instrument and detect that that instrument really will make this measurement of the sun if the sun acts the way we all believe it does, to the best of our knowledge. So we had to dive through the literature, look at things like how bright are these inhomogeneities in the outer corona? How sensitive do we have to be to see them? How small are they? What's our resolution? What's our field of view? We said it has to be at least 270 degrees around the sun. We did that so that we were sure that we would get at least the equator and one pole, right? Because it doesn't matter where that 270 degrees is located. You're always going to get at least one of those things, one of those two things. Time span. How long do you need to observe for to address that question? The spatial resolution here. Okay, so having done that, now you got to go the other way. You got to say, not just how do I make my instrument do this, but how do I close that? So what am I going to get from those measurements? Well, here I'm going to get the solar wind speed at least 4 radial positions 4 times a day. Is that enough? It turns out that is enough to close that question. We might get more, right? It might be useful for more things. But if we do this, we will at least be able to get that. And then from that, we'll be able to determine the solar wind flow. So each row of this describes that complete circle for one of our questions, right? We spent a long time looking at that, but this is important because all of these are all about what we plan to do. This is where we get the requirements on the mission itself, right, from the actual measurement. All right, so over on the right-hand side was another box that talked about how these oh yeah.
The minimum was 270 and then you have 360 for field of view, I think. How
Yes.
is that kind of industry minimum set? I think it was the slide before this one.
This one here, the 270?
Yeah, I think that maybe the slide before when you had, I think it was maybe when you had the picture as well. Sorry, go forward.
Here.
Okay, I can't remember where I saw it, but I can't, somewhere there was maybe when it was, oh yeah, here. Was it here? Yeah, baseline requirements, sorry.
Oh.
So yes. On the right-hand side, so like the field of view for the azimuth, I'm guessing that's azimuth, says like
yes.
Baseline requirement is 270. How is that baseline decided?
Oh, great that you're asking that question. Your check is in the mail. So this is where we are now, right? There's the requirement. Okay, and so this was part of our proposal. So these are the requirements that we got from the center of the traceability matrix. Okay, so if we make a measurement that satisfies all of these, where in each row we've taken the most stringent of all of those questions, then if we satisfy that, we'll be able to answer all the questions. Okay, and then over here, we racked up our design and we said, this is what our design should be able to do. And so this is a way of demonstrating our design will at least meet or exceed all of these. Yeah? Good. So that difference there, the 360 versus 270 is margin, right? How do you make sure you're going to meet a requirement? You do better than the requirement, and then what's left over is a little extra margin. And the margin is critical because as a PI in development of a mission, if you have margin, then if something goes wrong, and something always goes wrong, you know where you can trim stuff back, right? And so in this case, if we had something go wrong, say in the coronagraph, and we needed a larger pylon to hold that occulter, it might have obscured part of the field of view. But we knew we had 90 degrees of margin, so we could actually build a bigger pylon if we had to. Yeah. So this is a really useful tool. Do we want 360? Yes, but what do we need? Okay, now for a NASA mission, it's even weirder than that because these are our baseline requirements. That's what we're designing for. But they also ask you to design threshold requirements. Those are requirements that if you meet those, if you don't meet those, the mission's not worth doing. Right? So the threshold requirements are something that if I have to eat into my baseline and do worse science than I proposed, how bad could it get before you should just cancel me? Right? And so we'll talk about that in a moment. Okay, so these things lead to these 6 requirements, and this flow sort of shows how that goes into defining the mission. So our cadence here and our field of view gave us this 1+3 mission architecture with 1 coronagraph and 3 wide field imagers. And the various other blue boxes here are mission definition requirements that set the mission as a whole rather than just the instruments. All right, I'm going to walk you through a presentation I gave during our system requirements review shortly after selection, just to show you how all these things fit together. And the reason to do this is partly so that you can see that humans made this happen, right? It's not just an eye chart that we threw up there. We really thought about it. And the other is so that you realize what goes into making a traceability matrix. The reason people hate them is they don't know how to make them. The reason they don't know how to make them is it's like an iceberg. 4/5 of the work is hidden. What you see is that eye chart, right? But that eye chart is there because it's condensing a ton of work. In this case, here's our beauty shot of the high level objectives, right? And then these are the questions that you just saw written in topic form. This is what we did to define our level 1 requirements. The BSRs here are those baseline science requirements. That's the observing requirements that we developed and that I just showed you. There were 6 of them. Okay, so we identified our science question. We did that 6 times. We figured out what we had to do to address each one. In order to do that, we had to dive into the literature. We had to look at things like how fast do CMEs evolve? What do shocks look like? What's our best guess about the turbulence that forms in the outer corona? So we dove through the literature to find the best guess of what we were looking for. We cross-compared all those requirements to find the most restrictive requirement, and that formed our BSRs. Then we did that whole thing again to say, how for each question, how bad could we go and still say that we've made a significant advance in understanding? And we did the whole process all over again, and that gave us our threshold requirements. That merged with some other level 1 requirements levied by NASA on mission lifetime and things like that. And that is the wellspring from which all of our requirements flow, all the way down to how tight do you turn the screw on the door that's closing off Wi-Fi during launch. So our basic requirements were field of view, resolution, sensitivity, polarimetry. We had to have a requirement for some items to do polarimetry, spatiotemporal coverage, and mission duration. So those are the 6. Where did they all come from? Azimuthal coverage, I already mentioned it. It came from the fact that we had to get at least a pole and the equator. And so here we talked about there's fast and slow streams, and we have to see how we have to span both polar and equatorial regions. Right, that was the requirement. Radial coverage. You saw this movie yesterday, this polar coordinates movie. What I didn't call out is all the interesting changes in this movie happen in the gaps between telescopes. Right, that's how the world works. If you have 2 different telescopes looking at similar things, all the interesting stuff happens in the gap between them. So we had to have a seamless field of view that covered this region. And why did it have to be there? Because we knew on the inside of this field of view, you're looking at the corona. On the outside of this field of view, you're looking at the solar wind. So we wanted to span that boundary. Angular resolution. This is driven by a bunch of stuff. Everything had a driver. We had different spatial resolutions for every question. It turns out this is driven by 2. One is measuring turbulence in the outer corona, and the other is measuring the structure of shock fronts. There were some really interesting simulations that showed that shock fronts may actually be crinkled and rough in a way that we can't resolve with current coronagraphs. And that drove our resolution requirement, was to be able to see structure forming in shocks. Yeah, here we go. And so we specified our resolution at 2 places, one in the outer corona and one inner heliosphere. So resolve the flocculi, that's these turbulent structures. And out here, we had faint features marking the alphane zone, but it was a tie between flocculi and shock structure for what's driving it. Why do we need polarization? Polarization gives us three-dimensional information about the corona and heliosphere. I didn't show this diagram yesterday, but the polarization lets us measure this scattering angle chi, which lets us solve this triangle. Epsilon here is E for elongation. That's the distance from the sun on the focal plane. We're looking at the sun this way. If we see an object up here, some distance from the sun, apparent distance, we know this scattering angle. We now have two angles and a side of this triangle. We know the whole triangle, right? That's high school geometry. So by measuring polarization, we can actually determine where features are in 3 dimensions. So that drove our need for polarization, but also the photometry, because it turns out if you want to measure that angle, you got to know how bright the two different polarizations are. So you have to have a certain photometric sensitivity in each channel. This is a diagram just showing where that requirement came from. We didn't just make it up. Here's our photometric requirement. This was really interesting and hard to write. The reason is, and you'll run into this sometimes, we had multiple requirements for signal to noise ratio or bright photometric sensitivity and spatial resolution. It turns out they're coupled. If you can see something bright and large, well, sorry, bright and small, that's the same as seeing something faint and large, because large things cover a lot of pixels, right, on your image. But each pixel samples the noise field independently. So if you're averaging over a lot of pixels, the noise gets better by root n. And so if you can meet a photometric requirement for small things, you can way exceed it for big things. And it turned out we had to develop a whole formalism for comparing that. That's what these diagonal lines are here. Here you're seeing apparent feature size, which is our spatial resolution requirement, and sensitivity here this is 10 to the minus 15 times the photospheric radiance. So the apparent surface brightness of the photosphere, it's pretty darn bright, but times 10 to the minus 15, that's not very bright. And so these diagonal lines then are ISO lines of sensitivity in the instrument. We had to develop that formalism. Here's some justification. Spatiotemporal coverage, that was hard because we knew we wanted to say we just need every 4 minutes for everything. Well, we couldn't do that. We would have needed 5 or 6 or 7 spacecraft to do that. We couldn't afford that. So we had to really scratch our heads and think, well, how much resolution do we need in time in each part of the field of view? And so this is very complicated because it's reflecting the fact that we had to go back and scratch our heads and refine the requirement. We started out with, oh yeah, that ought to do it. And it turned out that was hard. And so we had to go back and figure out what we really needed. And we did that, and then we were able to meet that with the design. Here's some maps that we had to make, just showing how good the spatial coverage is. The color here is showing you how well sampled each part of the field of view is by the constellation as a whole. This on the left is in the nominal configuration. Over on the right here is if there's some orbital drift, which of course there will be. They're not rigidly attached to each other. They're flying in space. So we had to demonstrate that that would work. Here's some more diagrams just showing how our temporal resolution works in different parts of the field of view. I'm not going to cover that. Polarization, I talked about where that came from. We needed to measure these things in 3 dimensions. Mission duration. How do you know how long you got to fly? I don't know, till we're done. So we had, what it turned out what drove the length of our mission is the number of CMEs we had to see. So we looked at the solar cycle and how many CMEs there are per day in different parts of the solar cycle. We found the analog period from the last solar cycle and estimated how long it would take to meet our mission requirement in CMEs. Now, you never levy a requirement on your instrument based on the sun. You never say we have to operate the mission until we've seen 10 CMEs. You can't do that because that depends on what the sun does, right? You don't know if you're done, and it depends. I mean, the sun might not give you any CMEs that year. So you have to take your best guess as to what the sun will do and then levy the requirement on, we have to last long enough that we would have seen it. Uh, all of these things have uncertainty in them. If you build anything, engineers will tell you that, everything has uncertainty, so you have to tolerance that. Well, there's scientific tolerance too. Going from our level 1 observing requirements, which were justified from the science literature, we had to take into account the fact that the literature itself is uncertain, right? We're pushing the envelope. We don't actually know how the sun's going to behave. And so we gave ourselves some margin in the mission definition to account for the fact that the science was not entirely certain yet. And then we carry margin on each requirement when we move to the next lower level. Excellent. So managing 2 high-level requirements. Once you've got your science definition process and your traceability matrix, you make your level 1 requirements, and you flow them down level 2, 3, 4, and in a mission, it's down to 6. But if you're laying out an investigation where you use some code in a certain way, you may just list the requirements at the top level. You may not need to refine them. But if you have a large team of people all working on some major project that's going to use 100 person years, then you have to divide it small enough that each person working on the team knows when they're done. All right, so that is how we designed the Punch high-level requirements, which were then flowed down, and we used that to design Punch. And at the end, we actually verified all of those. We went through and verified the level 6s and rolled it up to the level 5s and so forth, until when we delivered the mission to Vandenberg Space Force Base to be bolted to a rocket, we had actually rolled up several thousand requirements and showed that they all worked. So not every traceability matrix looks like the Punch one. Cubics is one of these CubeSats that I talked about earlier. It's being built by Amir Caspi at Southwest. He gave me permission to show you his traceability matrix. This is for a smaller mission. It's a mission nonetheless. It has the same structure topologically, but it looks different. And so what I want you to see here is that the appearance of the traceability matrix is not the important thing. What's important is the flow. So in this case, he started with a physical parameter he wanted to measure. Right, here's his science question. What are the origins of hot plasma and solar flares? He's going to measure these physical parameters, abundances of various kinds of ion in these hot X-ray lines. And to do that, he's going to look at spectra and spectral images. His result is, here, this is his closure. He's going to get better understanding of the flare heating mechanism, or he's going to get robust analysis techniques for spatially resolved spectra. So this is a mission objective, and this is a technical objective demonstrating this method. Well, this was too wide to fit on a page, so he expanded here into his requirement, performance, and justification. That's very much like what we did in Punch. It's arranged slightly differently because he didn't have as many requirements. So he didn't have to work as hard at organizing them, but he did work very hard to show where they fit into this flow. So on the page, they're laid out differently, but he's used graphics here to show how they all fit together, right? And so then these are the equivalent, these are the measurement requirements, right? And this is sort of a description that we didn't have in that table of why you need that requirement. We broke it out into the text, but here he used an even more compact form. He didn't have supporting text. He just put the justification there. Well, he did, but not broken out individually. And then we had that table on the right that flowed things down to the top level mission requirements. Instead, he just drew a little arrow here and showed how it fell out, right? So this is another layout method, but really it's doing the same thing. It's connecting the dots from the high level question all the way to closing the science. This is how this mission will close the science. I hope you're not all asleep yet. I'm just going to give you some closing thoughts. So you need traceable requirements. They let you know, will this mission succeed? Will this project succeed? And when am I done? That's really important to formulate those, even if you just write them down in your notebook, so that you have a firm stake nailed into the sand, the shifting sands of the intellectual milieu where we work, right? So that you know when you're done. Traceability and requirements are essential to the process. If you aren't working to a traceable investigation, even if it's just in the back of your head, then you're just engaged in a hobby. You're not actually doing science. Traceability matrices define and communicate the requirements. So by learning to use them, you will do better on your proposals and your science will get better. Requirements are a roadmap for any scale. And I showed you two ends of that scale, right? CAPE-CORE, where I didn't actually show you the requirements, but I asserted that we had some. We had 4 observing requirements that drove CAPE-CORE. And PUNCH, which had, gazillion. Explicit requirements tracking is useful for small projects. If you can actually write down a set of requirements and check them off, it will make your project better. But they're essential for large projects. Just doing things off the cuff doesn't scale. You might get away with it at the small level, but you won't at the large scale. That's it. Thank you. Go forth and be productive. Yes, ma'am.
When you're like, so for Punch, when you're thinking about your science questions, so you said that there were 6 science questions for Punch. How, I'm also assuming that within those 6, they're broken down into like smaller sub questions than the big question. Deciding that it's 6, is that kind of depending on like the amount of money you're applying for? Like, how did you come to have 6 different science questions?
We chose 6 because those 6 spanned a large part of the community. That is to say, a lot of what we as heliophysicists are paying attention to is spanned by those 6 questions. But they are no broader than they have to be. As an example, right now we are working on a campaign to observe an interstellar comet. It turns out we'll be the only instrument that can routinely observe that thing for 2.5 months this fall. We are not required to do so. It just turns out that happily, now that we're on orbit, we can do so. But that doesn't mean people didn't come to us during development and say, gee, can you look at this or that or the other thing, right? There's a lot of stuff that people would like to do. And the answer is, well, maybe, right? But we're not required to do it. So we're not going to pay any attention to it until we're flying and know whether we have the resources to even answer your email, right? Because what we're doing is what we said we would do. That's an extraordinarily powerful tool because, I mean, I'm like you guys, I'm a scientist, right? I get really interested in stuff. Hey, wow, we can see the aurora? That's neat. Let's go look at. No, that's not what we're doing, right? Yes, this mission can observe the aurora. If somebody wants to use our data, look at the aurora, I'm all for it. If I have to do anything to support that, then I have to think about, is that in the budget, right?
How do extended missions work? How does extending it work? Because that's not something that's put out beforehand. It's just something who starts that conversation?
So NASA has a process called the senior review process, where every mission gets competed for extension. And so you have to propose the science for the extended mission as if it were a mission. It's less expensive because you don't have to build the hardware from scratch, but you still have to justify, this is how we're going to change the field or continue important continuous science by continuing to operate this mission. So nothing's for free.
Thank you.
Thanks. I guess to play off of that, so how, whenever you're designing missions, do you have like a time frame in mind of, well, it should last at least this many years, and then whatever we get on top of that is good?
So there are 2 answers to that, right? One is, I'm human, and so I have a sense of how long something's going to take. But the other more formal answer is, as a PI, when I'm wearing the hat and the pin, no, I have to go in with no idea how long it has to last until we've analyzed the requirements, right? Look at the science requirements, trace it through, figure out how long it has to last because of that, right? And if it turns out that that busts some other limit, NASA doesn't like really to select missions that take more than a couple of years. They do, right? Planetary missions routinely take a decade or more. But in heliophysics, typically a couple of years is about the right sweet spot. So if you can do something in a couple of years, it kind of behooves you to aim there. But on the other hand, you really need to go where the science leads you. If it turned out we needed to observe for a whole solar cycle, we would have said we can't achieve full success until 11 years.
And then how long does it take for this part of like the planning part of a proposal, and then like what the second part is actually making it if you get.
So how long does all this take? Overnight success in any business takes 5 to 10 years.
Okay.
So our first science definition meeting for Punch was in September of 2015, so almost exactly 10 years ago. we Punch was the 7th time I proposed a mission of this general type. All right, there were CubeSats, there was a space station instrument, there were balloon instruments, and every one of those failed, right? Was rejected for one reason or another. If you're going to succeed in a business like this, you have to learn from that, right? We talk about peer review and how important that is, right? The opposite of love isn't hate. The opposite of love is ignoring people, right? So if a scientist rips your work to shreds, that's actually really great. That's a sign of respect, right? So if you put together a proposal and you get good feedback on it, but it loses, that means that you as a scientist have just learned a whole bunch of stuff, right? And so by the 7th time we proposed this mission for Punch, we knew very well how it had to be structured and where all the weak points were. And we'd address them. There was an interval of about 4 years between 2012 and 2016 when I published 1 or 2 papers a year, which were all about addressing weaknesses in earlier versions of this proposal. Right. My favorite was we kept getting this criticism time after time. You can't do this kind of imaging from below the Van Allen belts. Right. The high altitude aurora that SME saw is going to get in your way. You can't look through it. So I went and got some internal money at Southwest to build a heliospheric imager and mount it on the roof of my house. And we demonstrated that it could see CMEs far from the sun. Not well, right? But my house is below the Van Allen belts, right? So we were able to demonstrate, but it took, so if you count that way, when did we start trying to build this mission? That was 2011. So it takes a very long time. That's because this stuff is hard, right? So if you want to succeed in any part of science or really in life, right, you have to have that persistence.
Oh, I'm just gonna go here and then put it.
When you propose an experiment and it goes for review, so I suppose that the reviewers would be also experts in the field, right? So is the review process a double-blind peer review or something like that? Or because I suppose even those reviewers would have their own experiments that they would like to push, and this could result in some conflict.
So the question is, how blind is the review process, basically? Yeah. And the answer is sort of and not very. Sort of in the sense that, especially at the grant level now, there's a big motion toward double-blind peer review, right? Where you don't know who the reviewers are and they don't know who you are. It's important that you don't know who they are so that they don't fear reprisal. But it's also important maybe that they don't know who you are, right? So that they can't play favorites in the community. And that's not because people are dishonest. It's because everybody has a natural inclination, right? These unconscious biases. We as scientists we osmote. We are not explicitly trained in how to engage as scientists in the community, right? We allow our ideas to compete with each other. And there are certain rules that are unwritten and largely unspoken about what is fair game to engage with. And those rules have gotten tighter over the years, right? We should engage with one another's ideas, but we shouldn't play dirty with them, and we shouldn't attack anybody personally, right? Science works best when our ideas duke it out and we all go have a beer together afterward, right? But the competitive process is a place where just naturally the worst elements or the least compliant elements of human nature come to the fore. And so that anonymity is really important. On the other hand, for something like a mission, right? Everyone has put so much effort into it. It's understood at some level that people have to separate. The process is just so over the top because the amount of resources it takes to put something in space are so large. So when we had our site visit, we met the reviewers for the site visit. For a mission, you propose, and then usually there's a competitive down select where they'll pay you to do a concept study. And that's where this traceability matrix appeared. And then people will come and interview you and talk to you about your science and the mission and make sure that they have a chance to ask you questions. And the reviewers are right there, and they're your friends and colleagues whom you haven't seen in a year, maybe. And it's understood that you won't hold it whatever comes out against them, and vice versa. And so there's an element of trust at that level. But by and large, it's anonymous.
Another question regarding designing an experiment. So when you design an experiment, do you take care about redundancies? So if one instrument fails, then the other could back it off. And if you do it, then how does it feature in the cost matrix, as in the trade-off between the cost and the science objectives that needs to be fulfilled?
They're brilliant questions. Redundancy is a way to make missions more reliable. It's a very expensive way because spaceflight hardware is expensive. And the most expensive part, it turns out, isn't the hardware, right? It's the human expertise. That's the one thing that you can't scale out of, right? You can make iPhones cheap by making 1 million iPhones, right? We all have phones in the room, and millions of those have been made. And so the human expertise that went into making them is amortized over every single phone. That's why they cost a few $100s. But with a bespoke space mission, you might use 30 engineers working for 2 years to design the thing and make sure that the whole system fits together, and you build one, right? And so that's very expensive. So redundancy is expensive. We worked very hard on resilient mission design. We tried to design a mission in such a way that if anything broke, there were a few places that were redundant, but mostly we could just try and fail softly. This was alluded to the other day, right? So we've actually done that. Our NIFI on Punch had a radio fail in the water, right? Because you can't talk to the spacecraft, it can't talk to you. Well, we had 2 radios on board. They're different. There's an S-band radio that's used for commanding and an X-band radio that's used for high-speed downlink. And the X-band radio actually failed like a couple of months before launch in thermal vac. And I made the call to just switch it off and never switch it on again. So that spacecraft now talks to the ground through only its S-band radio. And the cost there is we have to have more passes because we can't downlink as much data per ground pass, but it still works. So that's not redundant, but it's resilient.
And just like how if there's a software glitch, or you can send a software patch to fix it up.
Absolutely.
Are there any ways that we can fix hardware, maybe through a modular design in the future?
People work hard to design hardware that they can fix basically by turning it off and on again. Where have you heard that before? Or shaking it, and it's limited what you can do, but there are things you can do to try and shake hardware into a working mode again.
Thank you.
I see some questions in the back. You've been pretty patient. Sorry?
We got time.
Sure, for you.
Thank you, I'm honoured. One very quick question. You used the term hard and soft money at the start of the presentation. I don't understand the difference, and I'll ask the second one as well. How does the budgeting actually work? Is there a class of mission you aim for which has, say, $100 million, or do you go the ground up and then say this is going to cost this much and try and propose that?
It's more the former. So first things first, hard money and soft money. Hard money is money that just shows up and pays your salary. Soft money is money you have to go get. And so most federally funded science in America has been soft money for a very long time. That's part of why everyone's so worried about the NASA budget, right? It's a large fraction of our scientific community, at least in astro and helio, and really across the board, is funded by these grant programs that are under threat right now. In terms of mission size, you start out with a rough idea of how much a mission might cost, and then you try and tune it up or down, usually down, to fit within a cost cap. So the program that Punch was proposed to is called Small Explorers. It has a strict cost cap. In 2017 dollars, right, accounting for inflation backwards, I think it was $115 million. If we went over that by even $1, they wouldn't select us. So we had to work very hard to try and get in the box. We were pretty pleased with ourselves for getting 4 spacecraft for that price. It was pretty good.
This looks like a lot of work even before you get anything accepted. So how much is, up to the proposal step? I think you said earlier the matrix, the traceability matrix was some, partially funded beginning down select or something like that.
So the way Small Explorer works is NASA requires you to do your own initial study, right? That's called a step 1 proposal. And that's done at your expense. And they might get 40 of those. And then they'll order a handful, maybe 5. And those 5 then get concept study money. So they'll give you $1 million to go fund 10 or 20 people to do the engineering and put together a 300 or 400 page document that describes the mission. Now, that's a sucker's bet too, right? You don't do that to make money. In particular, if you want to win the mission, it's a losing proposition, because putting one of these together that will win is a $2 or $3 million exercise, right? So NASA's kind of helping you out. They're giving you some earnest money, if you will, to show that they've got some skin in the game, but they're not paying for the whole study. Then after that, the funding comes once you're selected.
Sorry to just follow up with that. If you're soft money funded and you're having to spend money to get these proposals, I guess you're writing, sub proposals, smaller grants to just propose this mission.
So you're not allowed to use NASA grant money to propose to NASA. But you are allowed to use institutional funding. And so the way federal dollars work is you charge real costs, hours, materials, things like that. But you're allowed to place a certain regulated percentage on top of that as overhead, the cost of keeping the lights on, paying the secretarial staff, things like that. And that's all just rolled into that overhead budget. And so large institutions pool that. Southwest Research, for example, we're a nonprofit. But certain sectors of the company show an alarming tendency to turn a profit. And so Southwest pours that back into internal research funding. So when we learned that we had gotten a step 1 award to do phase A, we went and proposed to that internal pool of money to support that effort. But no, you can't use grant money to try and get more grants.
I had a quick question about the traceability metrics. So how exactly do technological limitations factor into the metrics? Like, for example, for a science question, I might want the best possible spatial resolution and temporal resolution, but it may not always be possible with the existing technology. So do we have to sort of factor in mind what is possible before we sort of ask the questions?
I remember I was a young man at one time, and I would frequent speed shops. Imagine that. And I remember my favorite supplier had a poster behind the counter there. You'd buy your chromed auto parts there, right? And there's a speed costs money. How fast do you want to go? Right? Short of fundamental physical laws, it's always about the money, right? You've got some fundamental limit that hasn't been exceeded by people yet. That's okay. All you have to do is spend enough money and you'll beat that, right? I mean, that's sort of what we do as a species. And it's a big part of why NASA exists, right? Is we are a brain trust for the nation as a whole, pushing technological limits. And I mean, that goes all the way back to this post-World War II philosophy that federally funded research helps the nation become great. And so pushing the limits is what we do, but you have to know how hard to push the limits because pushing them costs money. And that's why you have to have requirements. All right. Oh, one more.
To hire people to begin with, or do you kind of work with what you have and then hire once you get?
It really depends. As a budding PI, you have to go out and meet people, and you have to learn very rapidly how to trust people, because early on, these missions are small, and you can know everything about it. But very rapidly, you get to a stage where you can't possibly know everything. You have to trust the people around you, and so the forming teams is an art. You could talk about all day separately, but it's all about finding people with good expertise whom you trust and like, because you're going to have to work with these people for a decade, right? And it's a high stress affair. So you want to be around people you like.